In this video, we will look at a problem that asks you to compute the number of arrays of length n, where the LCM of all the elements is equal to k. Along the way, you will learn some important techniques that deal with LCM, and you can apply these techniques to future LCM as well as GCD based counting problems. Let's just start with the solution. How do you compute the LCM between two numbers a and b? First of all, we write the prime factorization of a and b, and you can assume that both a as well as b have these all the prime factors in them. So you can write a as p1 to the power x1, p2 to the power x2, p3 to the power x3, and so on up to, let's say, pi to the power xi. Now here we are not making any assumptions about the prime because we can assume that all the prime numbers are present in it. For example, the representation might as well be the series of primes in order 2, 3, 5, 7, 11, 13, and so on. Because if a certain prime is not present in the uh, prime representation in this as a prime factor, then the exponent will simply be 0. So that is why for all the problems that deal with GCD as well as LCM, you can always assume that all the prime numbers that exist, they are there in the prime factorization of the number. So this means that A will have this form, but B will also have this form where B will have all the PIs. So B will have something like P1 to the power Y1, P2 to the power Y2, P3 to the power Y3, and then Pi to the power Yi. Now, in this LCM representation, in this prime factor notation, what is the LCM of A comma B? So by definition, the LCM means lowest common multiple. So for each prime factor, it will be simply Pi, or let me write that down explicitly. It will be P1 to the power max of x1 comma y1 into P2 to the power max of x2 comma y2, and so on, right, up to pi to the power max of xi yi. And why did I say that this problem will also help you with future GCD based problem? Because GCD of AB is nothing but product of pi to the power min of xi comma yi. So GCD is always the minimum factor that is appearing in both of them, and LCM is the maximum factor, right? If you are completely new to maths, it might sound counter intuitive because GCD has the name greatest, but then we are taking the min. But LCM has the name lowest, but we are taking the max. But remember that it is the greatest common divisor. So common divisor, of course, you can get by taking the min. But anyway, let's not dive too much into the details. This is basic number theory, so everyone might already know this. Like the LCM of any two numbers is the maximum exponent for each prime in the prime representation, prime factorization of that number. Now you can simply extend this logic to a series of numbers as well. You can as well say that LCM of A, B, C, D, E, etc. up to Z is nothing but product of pi to the power max, and then all the exponents like xi, yi, zi, and so on. So now the problem was asking you to find the number of arrays of length n with LCM k. So how do we solve this? So let's look at k. So if the LCM is k, let's look at the prime factorization of k, and suppose it is equal to p1 to the power x1, p2 to the power x2, p3 to the power x3, p4 to the power x4, and assume that there are only 5 prime factors for the number k, and then p5 to the power x5. Then you know that this result must have definitely come from this particular formula. So if you had like let's say element a1 over here, a2, a3, a4, and so on, then I told you that each number can contain all the prime factors that exist even though their exponent can be 0. So this actually helps us simplify some problems a lot. So here you can see that A1 will definitely contain all these PIs for sure, because even if it does not contain, its power can be interpreted as 0. And you can also see that A1 will not contain any PI that does not appear over here. Why is that? Because suppose it also contained P6, then while taking the LCM, the maximum exponent of P6 is 1. So P6 should have appeared over here. So if P6 is not appearing over here, it means that A1 can only contain these prime numbers, prime factors only. And maybe some of these prime factors might be nil, but we don't care. But we know for sure that each AI, right? The same argument is now also applicable to A2 and A3 and A4 and so on. So we know that any AI in the array can be written as P1 to the power Y1, where we still have to decide what are the possible choices for Y1, and then P2 to the power Y2 up to, let's say, P5 to the power Y5. Then you know that X1 is the maximum possible exponent in all of these AIs. In this, and this, all of these AIs have maximum. So means any AI cannot have the exponent greater than or equal to X1. So what are the possible choices for A1 when you are looking at this particular exponent P1? It can either be P1 to the power 0, it means that the prime factor is missing, or P1 to the power 1, or P1 to the power 2, up to P1 to the power x1. So how many choices are there? You can have x1 plus 1 choices. Then how many choices are there for this prime factor? In A2, you have this same x1 plus 1 choices. For A3, the number of choices remains the same. So you can see the total number of choices for making sure that this prime factor is accommodated in all the integers correctly. You can see that the formula would simply be product of x1 plus 1 n times, right? Which is nothing but, so you can simply remove this product and you can see that this is nothing but x1 plus 1 to the power n. But there is some corner case that we are missing. Remember that I told you that LCM is the maximum of all these, right? And we said that, okay, if it is maximum, then everyone needs to be less than or equal to maximum. But what if nobody achieves the maximum? So suppose if it is equal to P1 to the power 4 And when you were applying the choices, you said that the first element can be p1 to the power 2 p, and the second element is p1 to the power 3, and the third element is p1 to the power 0. But then their LCM would be p1 to the power 3 because max is 3. So we are not enforcing that the max has to be achievable, but we have to enforce that for the LCM to become p1 to the power x1 for this prime factor. So how do we do that? So you can see that right now we have made all possible choices. So we can subtract all the choices in which max is not achieved. And what are the choices in which max will not be achieved? Those will be exactly the ones where all the elements are strictly less than x1. So it means that AI can have the choices of p1 to the power 0, p1 to the power 1 up to p1 to the power x minus 1, x1 minus 1. So each element has x1 minus 1 plus 1, basically x1 to the power n choices. And in each of these choices, and since each of these elements are independent, that is why we are multiplying all of them, and that's why it's raising this power. So in each of these choices, since you have not used x1, right, the highest possible value, then all of these are the ones where the maximum x1 is not achieved and maximum is strictly less than x1. So if you subtract both of these, then the resulting ones are the ones in which maximum is for sure achieved, plus all the elements are also less than or equal to x1. And I hope you can see why we are taking the product, because each number will definitely have each of the prime factors, and as long as they respect the condition that pi is less than pi to the power yi is less than p1 to the power x1, then they will not interfere with each other because their final max is satisfied. So you can repeat this argument for each of these prime numbers, right? Each of the prime numbers that exist in the factorization. So therefore the answer to this problem is nothing but product of xi plus 1 to the power n minus xi to the power n. This is the final answer to the problem. And this xi is nothing but xi is exponent of primes. So that's it. That's the entire video. I just wanted to so this might be a very well known fact to some, and then completely new fact to others, like that LCM of a series of number is equal to the pi to the power max of each exponent for each prime, and GCD is equal to pi to the power min of the exponent for each prime. And using that we applied, I also showed you how to apply some combinatorics on it to figure out the number of arrays of length n where the LCM is equal to a given value k. Thank you.